Okay, so I'm J.J Biernacki, and I've been working at Tennessee Technological University for the past 6 years on a project that has been funded by the U.S. National Science Foundation on additive manufacturing of cement-based structures. And the project is in collaboration with colleagues at Vanderbilt University, Purdue University, and the National Institute of Standards and Technology. So it turns out that for about the last 80 years, the construction industry has been effectively stagnant, while other industries such as manufacturing, retail, and agriculture have grown by about 1,500%. And that stagnant growth really has been blamed in part on inefficient construction materials and practices. At the same time, there's a global housing crisis. About 1.6 billion people globally live in inadequate housing. 640 million of them are children. And it's not a problem that's isolated to the third world. 17 million United States citizens, that's about 5% of the population, live in inadequate housing. This house up in the upper right-hand corner here is actually a house somewhere in the United States. 40 million people, in addition to that, in the United States live in houses that they actually can't afford. But there's hope on the horizon, and it seems that possibly additive manufacturing of construction material could revolutionize construction in the near future and eradicate global housing. These two houses were additively manufactured with cement-based materials. This one in Austin, Texas, and this one in China on the opposite side of the world. So our group is actively interested in participating in any possible way that we can. But there are critical hurdles and gaps yet in the understanding that persist related to printability and printing of cement-based materials. So the material has to be extrudable. It has to be able to retain shape once it's deposited. It can't collapse under load of subsequent layers. It needs to develop good bonds layer to layer, and it needs to be a sustainable material. So our group is working on 3 particular areas, and we're not doing large-scale manufacturing. That is, we're not building large structures. We're working on a small scale, as you can see here, but we're actually interested in the science behind printing of cement-based materials. So we're working on material rheology, material selection, in particular for sustainability, as well as printability and material scaling. I'm going to talk about each of those areas in brief. So part 1 is on rheology, and this is actually the work of Babajide Onanuga, who recently graduated from Tennessee Tech. You know, I call here the strange rheology of cement and other particulate-based systems because the rheology of these materials really truly are quite incredible and strange. So I want to show this video. There you go. So I want you to look closely at what happens inside of a concrete mixer. When you look at this material that's being mixed, you can see that it cycles. There are shear cycles. It's not being sheared constantly when it's mixed at a single shear rate. It actually goes from being sheared at a very low shear rate to being sheared at a very high shear rate in cycles. But unfortunately, this is actually not the way that we ordinarily conduct experiments, rheological experiments, to make measurements of cement-based materials, or for that matter, for almost any materials. So I wanted to talk briefly about what happens when we actually shear a material under shear conditions like flow rheology. Okay? So this is a Newtonian fluid, and it's actual experimental data that I'm plotting here. A Newtonian fluid has a linear shear stress versus shear rate behavior. And as you increase the shear rate, the shear stress simply increases linearly. And when you decrease the shear rate in cycles, it decreases linearly and has no hysteresis. So the fact that the increasing shear rate and decreasing shear rate behavior is exactly the same makes it not only non-Newtonian but also time independent. But many fluids actually don't behave that way. Some fluids, like Portland cement and some polymers, actually have very complex behavior. If when you shear the material on the way up, increasing shear rate, the material tends to shear thin, and on the way down it tends to shear thicken, we call that thixotropic. But if the material tends to shear thicken on the way up and sheared thin on the way down, and we call it antithixotropic, and we'll wait for the next loop to show up. Okay, so in this case it's sheared thickening gently on the way up and sheared thinning on the way down, and that's antithixotropic. So this is actually simulated data just to show you how different complex fluids can behave. So what does Portland cement do? It turns out that if you look at Portland cement, the first cycle on the way up and the way down tends to be thixotropic-like, and it may not be classically thixotropic in that it's not exactly shear thinning on the way up and shear thickening on the way down. It's actually transitioning from a thixotropic-like state to a different kind of state. Usually what we do when we measure, when we determine rheological properties of Portland cement is we shear it up and then we shear it down, and we stop there and we analyze this down curve and we call it done for the day. And we determine properties, the yield stress and the plastic viscosity, let's say, using a model like a Herschel-Bulkley model. However, the truth is that if you continue to shear cycle Portland cement, just like is happening in the concrete mixer, what you find is that it quickly transitions from thixotropic-like to antithixotropic. And with additional shear cycles, what happens is you find that you have stable antithixotropic loops or stable limit cycles that are formed, as you can plainly see here. And this is real data for Portland cement being sheared in cycles. So the behavior of Portland cement under shear cycle conditions is actually antithixotropic and not thixotropic. Now that being said, we might be tempted to think that the transition from a thixotropic-like state to an antithixotropic-like state has something to do possibly with the admixtures we use or with hydration. That is the fact that the Portland cement is actually reacting with the water that's there. Well, this is a different case for deionized water. The shear conditions are slightly different than what I show, but what we see is a thixotropic-like initial condition transitioning to antithixotropic closed limit cycles. If we add superplasticizer, which is one of our favorite substances to add to make Portland cement flow better, what effectively happens is that we get a transition again from a thixotropic-like state to antithixotropic loops. The only difference is the antithixotropic loops have lower magnitude of shear stress when superplasticized than when not. Ammonium polymethacrylate is just another type of dispersion, and again we get exactly the same behavior as superplasticizer, only again the shear stresses are even lower than the superplasticizer. And once again, we have a tendency to want to say that this transition is somehow related to hydration of the cement and to blame it on hydration. So what our group has done is we've engineered a silicon carbide powder to look like Portland cement powder from a size and shape perspective. And we took a look at how does silicon carbide actually behave under the same types of shear cycle loads, a completely inert material in water. While Portland cement transitions from thixotropic to antithixotropic, silicon carbide does similarly. It actually transitions from antithixotropic to mixed mode thixotropic, antithixotropic. The bottom line is the complex behavior in Portland cement is really not due to hydration, but is actually just due to particulate behavior, at least up to a certain point in time. So what we did is to analyze the antithixotropic loops over a long period of time, continuously shearing the Portland cement. So we've captured just loops at 15 minutes, 30 minutes, all the way out to 120 minutes in 15-minute intervals. And we've plotted the shear stress at the maximum shear rate, and we've done exactly the same thing for silicon carbide. And when we take a look at how does the maximum shear stress evolve over time, for Portland cement you find this gradually increasing maximum shear stress with time, and you might be tempted to say it's hydration. But when you look at what happens with silicon carbide, a totally inert material, you see exactly the same pattern. This silicon carbide has characteristic particle size and particle shape that looks just like Portland cement. This is done in superplasticizer. And in ammonium polymethacrylate and superplasticizer have a same effective effect on both silicon carbide, totally inert, and Portland cement. We see the same behavior. Basically, these behaviors are actually related to particulate and not related to hydration, at least for the first 120 minutes and when the material is continuously sheared. So our conclusion with this particular work is that while cement paste exhibits complex time-dependent behavior and it transitions from a thixotropic-like state to an antithixotropic-like state, that behavior is primarily due to particulate interactions as long as the material is continuously sheared. This is not to say that static yield stress is not increasing because of hydration under static conditions, but under flow conditions, in order to model a behavior that looks like what happens to Portland cement under shear cyclical conditions, much like what we see in concrete mixers, we actually can pretty well ignore hydration as long as it's continuously sheared. So our ambition is actually to model this somehow. So we took a look at the broad literature, and there are many, many models in the literature, but we've latched on to one particular strategy wherein you start with a constitutive equation that relates shear stress to the shear rate and some sort of viscosity or viscosity-related parameter. But you modify that constitutive relationship by saying there's some form of structuration which can either form kinetically or be decomposed kinetically as a function of shear rate. So one particular model in that family of models has gotten quite a bit of has gained a lot of interest in the cements community, and so we've latched onto it, and we're going to explore how this model can be used or can't be used to model the particular behavior that we're observing in Portland cement. So the model that we're using effectively starts with the Herschel-Bulkley equation and does only a very simple thing. It modifies the yield stress term in the Herschel-Bulkley equation by adding a structuration term. And that structuration has a kinetic rate law that says it'll structure when at rest and it does something else when it's being sheared, okay? So let's take a look at how this actually works. If the structuration parameter at rest is positive and the destructuration parameter under shear is negative, what we actually see is a transition from a antithixotropic-like state to a thixotropic-like state, forming stable thixotropic limit cycles. And in fact, we see that the structuration parameter is bounded and reaches some stable oscillations as we reach these stable thixotropic limit cycles. Now, the structuration parameter is not bounded or necessarily has to be 1 or anything like that. This model does not prevent the structuration parameter from being much greater than 1. For example, as you see here, we have a structuration parameter as high as about 3. The question is can we make this model transition not to thixotropic behavior, but to antithixotropic behavior? So what we did is we explored what happens when we vary the signs on A-thix and alpha. So if A-thix is positive and alpha is also positive, what happens is that you continuously structure. Whether the material is at rest, that is no shear rate, or whether the material is being sheared, it continuously structured and the shear stress is always increasing. This is actually a possible physical condition. Imagine a polymer that's actually, or a material that's polymerizing and beginning to set. It's always structuring, and so the yield stress may be increasing continuously in it. And so it's not an unphysical condition. It's divergent in that it's always structuring under any condition, even when it's sheared. And in fact, even Portland cement, as it begins to set, we might say, well, maybe this has some utility even for setting Portland cement. So we then said, well, what if the A-Thix term is negative and the alpha term is positive? Could we get something that looks like antithixotropy? Could we get actually shear thickening at some point? And in fact, you actually see something like this. But what's happening is that the material in this case is always destructuring. And because it's destructuring, you actually can predict shear stresses that are negative, and that's not physical. The last case is that if A-Thix is negative and alpha is negative, we actually now see a transition from something that looks like thixotropy to antithixotropy, and we're almost ready to say we're good to go. But the problem is once again, you can predict negative shear stresses. And not only can you predict negative shear stresses, but the structuration parameter can also become negative. Now, while a negative structuration parameter might not necessarily be unphysical, the negative shear stresses are unphysical. So the bottom line with this particular model, which works very effectively to predict stable limit cycles that are thixotropic, it cannot predict the transition to antithixotropy from this thixotropy, and it has two particular sets of conditions which are unphysical, and a potential condition which is maybe physical for real unique situations. So what to do? So our group thought, Babajide and I, we thought, let's just think really conceptually of what's happening with thixotropy, for example, and what's happening with antithixotropy. We can think of thixotropy as the destruction and the formation of some sort of soft flocks. So we call those thixotropically associated flocks. As we shear this material, those flocks are destructured, and there's fewer of them, and the model that we're using from the literature is very effective at modeling that kind of behavior. And when we relax or reduce the shear rates, the flocks reform, and this model does a beautiful job at doing that. However, at higher shear rates and when those thixotropically associated flocks are mostly decomposed, you then develop antithixotropically associated domains. And this model in black and the original model in blue actually doesn't do a very good job, or doesn't do a job at all, at predicting the behavior of those thixotropically associated domains. So our hypothesis was that while the original literature model does a great job at modeling thixotropy, could we not add a second form of structuration that accounts for the antithixotropically associated domains? And so we're going to hypothesize that that form of equation for structuration might take on the form of a harmonic oscillator, and I'm going to explain why maybe that makes some physical sense. If we think of antithixotropy as the formation of thixotropic domains where particles are jammed together kind of rigidly, then we could think of this antithixotropic structuration as a form of storing up elastic energy, much like might happen in a harmonic oscillator. So you can imagine that strain energy, if you think of this structuration parameter as being somehow related to a strain, then you can store up strain energy in a spring with a spring constant, and you can dissipatively, frictional-based dissipation, which is related to the time rate of change in strain, and in this case, a structuration-related strain, and then that could be driven by some sort of driving mechanism, and in this case, the driving mechanism is related to the shear rate. So when we do this, what we find is that the two-mechanism model, the model which incorporates a good model for modeling thixotropy and what we think is possibly a good model for modeling antithixotropy, totally is able to capture the transitions from a thixotropic-like mode through transitional mode, mixed mode, thixotropic, antithixotropic, and then eventually form anti-thixotropic closed limit cycles, and it's very stable. This is actual experimental data compared to the computational model. And in this case, this third block to the right here is the structuration parameters for both the anti-thixotropy, end-of-thixotropy structuration, and the total structuration, 1 plus lambda 1 and lambda 2. And you can see that they're bounded, not necessarily bounded to 1. There's no reason that they have to be in these models, but they're positive, and we don't generate any negative shear stresses in this case. So at this point, we're quite confident that we have a reasonable model for modeling the observed behaviors. We have somewhat of a reasonable connection to a physical basis for that model. The second part of our work now is to actually try and select good admixtures for making, transitioning cement paste from being a really unprintable material to making it a printable material. And we're keeping sustainability in mind. We're trying to select materials that will be actually sustainable into the future. So once again, printing materials have to have good characteristics with respect to extrusion and bond building between layers, and et cetera, et cetera. And we can see that unadmixed cement paste is a terrible material to try and print. It's not that we can't print with it, but it is very poorly extrudable, and so we're searching for admixtures to use. So the world of admixtures is large. And there's many things that we can use off the shelf, like superplasticizers, which are favorite materials in the cements community, but they tend to make materials more flowable. We can use off-the-shelf viscosity modifying admixtures, which help, but they're mostly formulated for underwater applications and not actually for printing. We can add clays and limestone or supplemental cementitious materials like slag and blast furnace slag and fly ash and silica fume, and everybody is doing the above. But in addition to that, we recognize that hydrogel-forming polymers, which, by the way, are at times some of the ingredients in off-the-shelf viscosity modifying admixtures include these things. But we're talking about using these things in a much different way. So typical admixture problems include bleeding, as you can see here, which is a fairly well printing unadmixed cement, but it's still bleeding like crazy. Poor extrudability. You have big gobs coming out at times. No matter how well you shear the material, it's still poorly extruding. In addition to that, hydrogels, which are going to be our material of choice, they can be mechanically unstable. You shear them and they no longer have mechanical structure. Or they can be chemically unstable at the high pH of cement paste. So in selecting hydrogels, we have to down select for properties that we really want. Well, some of the properties of hydrogels that can be very positive for printing is that they can have extremely high viscosities, they can be very shear thinning materials, and they don't need to be inherently rheologically time dependent. They can be very nonlinear and very non-Newtonian, but they don't have to be time dependent necessarily inherently. And in addition to that, they can retain water and act as internal curing agents, which is extremely important for additively manufactured cement-based materials. And they can be very lubricating. So after a process of down selecting, we've chosen hydroxyethylmethylcellulose, hydroxypropylmethylcellulose, two polymer backbones which are sustainably sourced from plant materials, and then polyethylene oxide is a more traditionally sourced polymeric material that actually forms good hydrogels as well. So because we had no idea how these materials would print in advance, we thought we'd do a screening study, and so we did a 4x4x3 full factorial design where one of our parameters, we have a threefold parameter, which is the type of gel polymer, and then two fourfold parameters, one of which is the polymer content of the gel, which we call gel percent, and one of which is the gel to cement ratio, which is a surrogate here for water to cement ratio, and that's a fourfold parameter as well. We developed gel preparation techniques and proper paste preparation techniques, both of which are critical to get good printing outcomes. So we printed this large matrix of samples, and we then just put them visibly on a matrix to see how do these things actually compare, at least to the eye. And we immediately can see that hydroxyethyl methylcellulose is the best printing material. It gives us the highest print fidelity and has the largest domain of printability. These pale purple dots here are actually materials that won't print. They either won't come out of the printer or they just don't hold their structure for some reason. And so we have domains of non-printability, domains of printability, and domains of poor printability. And our question really at this point is, can we quantify this somehow? So at that point, the question became a quest to figure out how do you compare a printed object to the model that it was printed from. And there are lots of different techniques for doing that. Again, we tore into the literature and we found that there are really three groups. Semi-quantitative things like visibly looking at it and giving it a score. That's kind of a beauty contest, and it's not really necessarily the best representation. But a lot of people look at surface. Where is the surface of the printed object compared to the surface of the model object? And some people look at where is the volume of the printed object compared to the surface of to the volume of the model object, and we chose to look at both a boundary fidelity and a volume fidelity. The problem with all of those techniques is that you have to somehow align the printed object with the model object to be able to make some sort of quantitative comparison. So what's generally done is some sort of alignment landmarks called fiduciary points are chosen, but those are chosen at random. Where should you choose them, for example? And after you choose them, how should you align them? Should you align the base or the basal planes and then one point on that plane? Or should you align the centers of mass of the objects and keep the basal planes parallel? Or should you somehow rotate the object, align the center of mass and then rotate the object in such a way that there's a minimum distance between the fiduciary points, and then at that point say we're going to compare other points, the distances between those points and the surface of the model object. And actually we didn't like any of those techniques. So what we chose to do is to do two things: to align the basal planes and then the centroidal moment of inertia, the axis of centroidal moment of inertia, or we also chose to align the centroids and then to rotate the object until the axes of minimum moments of inertia are actually aligned. It turns out that this latter case, which is the most difficult one to do, is the most unbiased thing that we could think of doing. Now, I should also mention, for those of you who intend to do things like this in the future, that if you do boundary-based fidelity measurements on printed objects, you have to have some sort of statistical criteria. How many points on the surface will you measure? And so that has to be established. If you do volume-based techniques, you have to integrate the entire volume to compare volume to volume. So both of these things have their pros and cons. So what we're doing with our objects, because they're small, we can get complete CT scans of them. And all of our CT scanning work is being done at the National Institute of Standards and Technology at Boulder, Colorado by Ed Garbosi and Newell Mosier. And they've done a lot of work with us on scanning our objects and helping us understand how to do all these things. So we scan the objects, and then we do all these standard image analysis things that people do, like we sharpen the images, we threshold, turn to black, convert to black and white, we then obscure artifacts, and we then have clean binary images which we can create stacks from, and then point clouds. So this is an actual photo of one of our printed objects, and this is the digital point cloud rendering of that photo, of that object. Once you have the digital renderings, we can then identify the types of internal features and external features that there are and begin to make comparisons of, for example, volumes and surfaces. This is just a comparison. The blue dotted line is the comparison of where the model surface should be and where the actual printed surface is. So we then calculate a boundary-based printability index or fidelity metric by comparing many points along the surfaces of the boundaries and the boundary-based method is nothing more than a comparison of the location of the actual surface that's printed and the desired surface. And similarly, a volume-based technique which compares where is the area of a specific slice relative to the model area. How much of the area printed is outside that area, the desired area, how much of it hasn't been printed inside that area, and a comparator is made from that by integrating over the entire stack, in which case you're actually integrating the volume, the entire volume. So I said that the boundary-based techniques required sampling statistics, and I just wanted to show these two plots here. These plots show that for our samples, we're requiring a sampling of about 1,000 points along the surface, which is actually a very small number of points, in order to get a stable value of the printability index. That is, the standard deviation will shrink with as you increase the numbers, and it'll shrink to a point at which it is representative of the population for all intents and purposes. So we're sampling about 1,000 points along the surface when we do a surface-based technique. Now the question is, if you recall, we had two techniques, one of which we aligned the basal plane and then we aligned the centroidal axis of moment of inertia, and the other of which we align the centroids and then we tilt or rotate the object until the axes of minimum moments of inertia are aligned. That's actually a relatively difficult thing to do, especially for arbitrary objects. But nonetheless, the question is should we do that rotation or shouldn't we? Do we gain anything from doing it? And the fact of the matter is when you compare a boundary-based printability index for when we rotate versus when we don't rotate, you find out that rotation is absolutely critical to get sensitivity or to get information from a boundary-based technique that has something to do with the flaws that are inside the object's volume. So we can actually, because we rotate the object and align the axis of minimum moment of inertia, the boundary-based technique actually represents not just the fidelity of where the surface is, but it reflects flaws that are inside the surface, and it's the only way to see them. So that being said, we now have good techniques for measuring print fidelity, and we can quantify the print fidelity for structures that we've made. And using that quantified print fidelity information, we can then generate response surfaces and get some visual representation of which of these printing aids were better than the other. And of course, the naked eye says hydroxyethyl methylcellulose has the broadest printability domain, and indeed it does, with polyethylene oxide probably being the least printable of the materials, and the propyl methyl being somewhere in between. So with that being said, we began to adopt the hydroxyethyl methylcellulose as our champion material, and we wanted to study why is it that some domains are more printable than others? What about the actual physical properties of the gel and the actual physical properties of the gel cement paste that makes it more printable? So we plotted the boundary-based index versus the volume-based index as a way of trying to see how much better is the hydroxyethyl methylcellulose. And this type of representation clearly delineates how much that the hydroxyethyl methylcellulose is much better than the other two printing aids, which are almost identical with respect to print fidelity. That being said, what makes some domains, some formulations better than others? So what we've done is to use oscillatory rheometry to actually measure the elastic property of both the gel and of the gel cement paste. And what we find is that as we increase the polymer content in the gel, as one would expect, the gel material has a higher storage modulus. It becomes more elastic-like, right? It becomes more solid-like the higher the polymer content. But if you look at the paste made from those gels, it's actually the inverse relationship. As the polymer content of the gel increases, right? At a constant gel to cement ratio, the cement gel paste becomes more malleable. Actually, the solidus property, or the storage modulus, actually decreases. So how does this play out then in terms of printability fidelity, right? So if we were to compare the storage modulus of the neat gels to the print fidelity of the actual printed objects, what you'll find is that as the gel becomes stiffer, printability is increased. That is to say that the print fidelity is increased with increasing gel stiffness. If we do the same thing for the gel cement storage modulus, because there's an inverse relationship, what we find is that within certain limits, as the gel cement storage modulus decreases, the print fidelity increases. So if we put all of those things together, mapping both the storage modulus of the paste and the storage modulus of the gel together, we can actually find high performance domains wherein we can identify the actual property that the gel cement paste should have to give us high performance printability. So in this particular case, we've identified a domain that has as low as reasonable gel to cement ratio, because this is an analogy to water to cement ratio, and in order to keep mechanical properties of the hardened cement paste high, we want as low a gel to cement ratio as possible. And in order to not use more polymer than we have to, again, thinking of sustainability and the cost of that material, we want to have as low a gel content or as low a polymer content in the gel as possible. And we've picked a domain that actually gives us very high performance printing. So by trying to understand the science behind what causes good printing, we were able to correlate the viscoelastic properties of both the gel material and the paste. The bottom line conclusion here is that hydrogel forming polymers, if they're selected properly, are truly transformative. They can transform unprintable neat cement to printable cement. Now, granted that no one is actually going to print neat cements, but people are printing fine aggregate cements, and we expect that this will be quite scalable. And the next topic we're going to talk about is scalability and our work on scalability. So we have 3 papers that we've already published on this, and if anybody's interested in these papers, you can find them easily online. The one in gels is open access. The other 2 are not, but we'd be glad to help you with that or talk to you about it. So on scaling now, our question with scaling is really, we can print materials, and this happens to be us printing with neat cement paste, which is really hard to do, okay? But we can print if we formulate the paste right. You get the you get the water to cement ratio exactly right. You might print something with neat paste. So we thought, let's simplify this work and let's only look at neat cement paste printability. So we designed an experiment with a very broad range of water to cement ratios, and we had 2 pathways. One of which is the printing pathway. We printed with these different water to cement ratios, double-walled hollow cylinders. We then sectioned those the hardened cylinders. We polished the edges and we photographed those edges, and we got an experimental cross-section for the shape, the nominal shape of that printed object. We had a modeling pathway where we took these cement pastes, we looked at their rheology, we used a Herschel-Balkley or a Bingham-like model and extracted yield stress parameters and viscosity parameters and put that into computational constitutive modeling and did computational printing. And then we compared the experimental values to the simulated results. So we have a particular mixing protocol that we're using where we either mix the cement paste and print with it immediately, that we call paste A, or we mix the paste and we let it age for about 30 minutes. Then we remix the paste under a certain protocol, and we call that cement B, or the aged paste. There's evidence in the literature that possibly aging the paste has an effect on printability, and so we thought we would do that. So these are simply a set of curves for the unaged paste and the aged paste, and all we did here was to shear under our shear protocol. I think we did 5 shear loops, and then we took a down cycle, and we determined we fit those curves with a Herschel-Bulkley model or a Bingham model and extracted parameters. And these are just the extracted parameters. The thing to focus on really here is we've plotted yield stress as a function of water to cement ratio for the aged and the unaged paste. And you can see that clearly there is an effect on yield stress, which likely will have an effect, as we'll show, on printability. But below a water to cement, or above a water to cement ratio of about 0.4, there's really no difference between the aged paste and the unaged paste with respect to yield stress. So that being said, the next thing we wanted to look at is to see if static yield stress makes any difference, or if it's changing quite a bit, or how fast is it actually changing, and do we need to account for it in our computational models? So again, we went back to our same citation that we had been using earlier, and we used under static conditions, there's 0 shear, and that collapses then to that the yield stress is a function of this ATHIX parameter and time. And we actually extracted that ATHIX parameter from work by Jan, where he did very nice static yield stress work right in the domain where we're working, between 15 and 135 minutes for water cement ratios, which are very similar to ours. And we found that the value of the ATHIX parameter is actually very small relative to the time frame that we're printing. So we print so fast that the static yield stress buildup is really of no consequence. And later in the conference, Abdul Salam Mohammed will talk about actually including the static yield stress as a variable in the computational model. But for the models that I'm showing today, in this presentation, we're ignoring this buildup of static yield stress. So there's one last thing that we have to worry about. When we do computational modeling, models will actually approach a singularity as you approach the yield stress. So you have to somehow prevent that by doing something called regularizing the constitutive law that gives us the viscosity. And in order to do that, all we do is add a very small shear rate value to the denominator of either the Bingham or the Herschel-Bulkley model. And as long as this value is very small, what will happen is the viscosity will become very large, but not infinitely large, and it will prevent the singularity. And this sort of regularization, at least for the computational tool set we're using, works very effectively. So I'm not going to talk a lot about equations, but we're effectively solving the generalized continuity and Navier-Stokes equation, and we're using a level set technique to cope with the free boundary at the surface of the cement pastes that are being printed. So the first thing that we did was to try to make sure that our rheological data would predict the slump behavior of Portland cement. So we did macroscopic slump tests where we used a mini slump cone. We mixed the cement paste from 0.5 to 0.3 water to cement ratios, and then we compared the slump behavior of the model, totally uncalibrated, right? And it's validation, not actually calibration. And you have on this side the actual slump behavior of real cement, and on the right side the slump behavior from our computational model, which was derived from rotational shear rheology, flow rheology measures, no calibration against the actual slump. And we get beautiful agreement between the two. That being said, we were ready now to compare actual printed samples to computationally printed samples. So here again are our printed samples, and we then had to develop a technique so that we could computationally print. Computational printing using continuum-based models is very time expensive. So we developed a technique we call 2D stationary computational printing. So imagine you take a slice through the material that's being printed. What's going to actually happen? Imagine you can only see that two-dimensional slice. At some point in time, the printer will come past and deposit a first layer at time t1. And between the time t1 and the next time that printer comes past, that layer will slump under its own load, and a new layer will appear and print on top. And that will continue to happen. So what we are not doing is piling up a bunch of layers at time 0 and watching them slump. We're actually watching it being built in 2 dimensions, layer by layer, with time intervals in between each layer of deposition equal to the time interval of the passage of that printing layer. This we call 2D stationary computational printing. So here's the actual computational simulation showing each layer. We're printing a double layer wall, and each layer is printing inner and outer wall, inner wall. And as you'll see, each layer as it comes past, this is a rather fluid material. Each layer is wicked in to the substructure below, and you can see the slumping behavior of the structure as it grows. This is a 0.375 water to cement ratio. Its yield stress is 110 pascals. We're not changing that yield stress as a function of time because remember the ATHIX parameter is very low. At some point, and I'm taking time so you can see the complete simulation, this simulation will actually predict the failure point for this material. So as you see this swelling at the bottom, and layer by layer you see some variation, and all of a sudden here at the very top it will suddenly collapse under its own weight. So the question is how well can we predict this collapse? If we take a look at from a water to cement ratio of 0.3 to 375, above a ratio of about 0.4, we can't even print. It's so fluid, it just comes out like a liquid. At the low water to cement ratios, we have very excellent prediction of what the structure will actually look like, but we're also doing a very good job of predicting the actual print height and the shape of the print of the slumped objects, both for cement A, which is unaged, and for cement B. So in order to quantitatively compare these, we used the techniques that Tahiri had developed in the previous presentation, in the section 2 of the presentation, where we quantitatively compared what we should be printing and what we actually printed. So in this case, we aligned the basal planes and we aligned the axial centroidal moments of inertia, and we compare how much of the object we printed is within the area of where we wanted to print and how much of it is outside, and we come up with then a print index or a fidelity metric. And then we plotted the fidelity metrics along the yield stress curves which we earlier developed. And what we find is that we might draw an arbitrary line between high print fidelity and low print fidelity objects at around 0.7. And so we now have a quantitative metrics that tell us how well, what do these printed objects actually look like. If we compare the print index of the actual object to a print index of the model object, what we actually find is excellent agreement. It is not a one-for-one agreement. The model tends to a little bit over-predict the print fidelity, as we would expect. We don't have a lot of non-ideal behaviors in the model right now, but there's a very good prediction, and all of the data, whether it's aged or unaged cement, collapses on itself. One last thing that we did was to compare our work to the work of Suker, who has analytical equations to predict the height of failure, and our heights of failure by computational two-dimensional, the 2D stationary computational printing, and Suker's analytical equations match almost perfectly, and there's excellent agreement between these things. So we have high degree of confidence. The bottom line is, in conclusion, we think that our 2D stationary computational printing strategy is a very viable route for being able to predict printability, and we have a high degree of confidence now that we can actually use this kind of model to come up with scaling rules to say what happens when you make the print larger and larger, or for that matter, smaller and smaller. And we have one paper published already on the 2D stationary computational printing strategy. We have a second paper in review on extending the model to include the changing static yield stress work. And this was the work, of course, by Abdul Mohammed for his PhD dissertation. So I'm going to stop here, and we'll take some questions.